At this stage of your journey into calculus, you may have a number of unanswered questions. By now, you probably have estimated an area using Riemann sum. You may recall that a Riemann sum is an operation in which you select an interval over which you wish to calculate an area. You chop that interval into several pieces, construct a series of rectangular areas, and write a summation formula. You then determine the value of delta x and evaluate the Riemann sum over a specific interval with a set number of divisions and specific values for f of x. For example, this particular Riemann sum evaluates as follows. And expands as such. You can pause the video if you want to check my math. If my calculations are correct, you get the following answer. Pretty easy, right? However, suddenly, you are presented with an infinite series of rectangles, and your Riemann sum looks like this. Notice the limit as n goes to infinity. And you wonder, how am I supposed to add together an infinite number of rectangles? At which point you are told, no worries, you can simply change the sum on the right side to this, replace f of x with x, or whatever f of x happens to be. You can then take the antiderivative of f of x and evaluate it from a to b, which in this specific case evaluates from 0 to 3 and simplifies as such. If I had to guess, you got lost at this point in the explanation, the point where an infinite sum of rectangles somehow magically transforms into the antiderivative of f of x, and then evaluates as such. And you can't help but wonder, where did the antiderivative come from? And how is all of this suddenly equal to that? It turns out that many books tend to downplay the important role of this formula when discussing the fundamental theorem of calculus. To be more specific, this version of the formula is often downplayed. In addition to this, many books fail to make it clear that every function you come across when applying the fundamental theorem, every function, is treated as if it were a topographical map of another function. Notice that I have chosen to call this function little m of x. I am choosing to interpret this function little m of x as if it were a topographical map of an unknown function capital M of x. Let me continue this analogy. Suppose when Sir Edmund Hillary scaled Mount Everest, he was keeping track of how steep the mountain was at each mile marker between the base camp and the summit of Mount Everest. And for the sake of this analogy, let us say that little m of x is a plot of how steep the mountain is at each mile marker x. When I look at the graph of little m of x at x equals 3, I can see that little m of 3 is equal to 0. This tells me that when I get to mile marker 3 on the trail up Mount Everest, I will come to a nice flat plateau, which means that the slope of the trail at mile marker 3 is 0. I may not yet know exactly what the whole mountain looks like, but I do know that Mount Everest is flat at mile marker 3. I can also see that Mount Everest is quite steep at mile marker 8. For every mile I walk toward the summit, I have to climb up almost 5 miles. In fact, the more I look at little m of x, the more I learn about my unknown function, capital M of x. To quote a famous map guru from ancient China, the more you study the map, the more the mountain will reveal itself to you. But let us return to the mathematical question before us. How is the sum of an infinite number of rectangular areas under little m of x related to the antiderivative of little m of x? Let's now tackle that question. However, to answer this question thoroughly, I feel compelled to walk you slowly through another Riemann sum to show you how this version of the slope formula serves as a bridge between little m of x and our unknown function capital M of x. This exercise will show how a Riemann sum under little m of x is related to the antiderivative of little m of x, which for now we call capital M of x. For the sake of simplicity, let us estimate the area under little m of x by summing together a series of 8 rectangles. Notice that I am constraining little m of x to an interval between x equals 0 and x equals 8. In this situation, we are using a left-hand Riemann sum with delta x equal to 1. Adding in a few points will make it easier to find the area of each rectangle. To find the area of any rectangle, we multiply little m by delta x. Now recall the following formula from earlier, rearranged into a different form. Something familiar about the right side of that equation. It looks as if the area of one rectangle is equal to a change in y of our mysterious function capital M of x. Let's see if we can discover the identity of this unknown function. First, a little housekeeping. We can see that the value of little m1 is 1.688, and the value of delta x is 1. When we plug these values into the equations below, the area of the first rectangle on the left is 1.688 square units. And over the course of delta x, our mystery function grows by 1.688 units. Let's take a snapshot of this delta y line segment. Think of the rectangle on the left as if it were one bar on a bar graph. The height of the first bar on the left indicates the average slope of our mystery function from x equals 0 to x equals 1. But the area of this bar tells us the change in y of our mystery function. Let's look at the next rectangle in the series. Once again, delta x equals 1. The height of this rectangle is 0.75, which means that little m2 is equal to 0.75. And the average slope of our mystery function from x equals 1 to x equals 2 is 0.75. The area of this rectangle is 0.75, which means that the change in y of our mystery function from x equals 1 to x equals 2 is also 0.75. Let's now calculate the areas of the remaining rectangles, keeping in mind that each area on the left is equal to a change in y of our mystery function on the right. If we sum up all of the areas on the left, we are also summing up all of the changes in y on the right. Also note that the sum of all the delta y's on the right forms a line segment with a length of capital M of 8 minus capital M of 0. So we can now say that the sum of the rectangular areas on the left is equal to the length of the line segment on the right. When we expand the sum on the left side and then simplify the answer and round it to 2 decimal places, we can see that this produces the same value as capital M of 8 minus capital M of 0. Also note that the piecewise graph of capital M of x is beginning to resemble an antiderivative of little m of x. Let's see what happens if we get a better approximation of the area under little m of x. In this scenario, we will try a Riemann sum with more rectangles. In this case, delta x equals 0.5, and the number of rectangles is 16. Once again, it will help to have a few points to refer to. And we will need these two equations again. We will calculate the area of the first two rectangles and then fill in the rest automatically. The height of the first rectangle is little m of 0 equals 1.688, or as it appears in the area formula, little m1 equals 1.688. So the average slope of our unknown function from x equals 0 to x equals 0.5 is 1.688. However, because delta x equals 0.5, the area of the first rectangle is 0.844 square units, which also means that delta y is equal to 0.844. Moving on to rectangle number 2, we find that the height of the rectangle is 1.172, which means that the average slope from x equals 0.5 to x equals 1 is 1.172. And again, delta x equals 0.5, which means that the area of the second rectangle and the change in y of our mystery function both have the value of 0.586. When we calculate the remaining areas on the left, we can represent these areas as changes to the value of our mystery function on the right. And once again, the sum of all the areas on the left is equal to the sum of all the changes to y on the right, or capital M of 8 minus capital M of 0. When we expand and simplify both sides produce the following result. Notice that the sum with 16 rectangles is a little greater than the sum with 8 rectangles. Also note that each area across delta x is smaller, which also means that each change in y is smaller. However, as delta x gets smaller, the number of rectangles increases across a given interval, which means that there are more changes to y crushed into the space between capital M of 8 and capital M of 0. In fact, no matter how many changes of y we smash in between capital M of 8 and capital M of 0, the sum of those changes in y will always be equal to capital M of 8 minus capital M of 0. Watch what happens as we shrink delta x and increase the number of rectangles. I have included the antiderivative of little m of x for comparison. Here we have delta x equals 0.5, and there are 16 rectangles. Here we have delta x equal to 0.25, and there are 32 rectangles. Delta x here is 0.10, and there are 80 rectangles. Delta x here is equal to 0.05, and there are 160 rectangles. And finally, delta x equals 0.01, and there are 800 rectangles. Notice that our piecewise function capital M of x approaches the antiderivative of little m of x. Or we can simply say that capital M of x converges to the antiderivative of little m of x. Now recall that every rectangle we construct under little m of x that has a uniform height across delta x can be thought of as one bar on a bar graph that shows the average slope of m of x across delta x. So what happens to the average slope of a function as delta x approaches 0? Perhaps this version of the slope formula looks familiar. As delta x goes to 0, each rectangle on the left becomes infinitesimally small, while the average slope of the line segment on the right becomes the derivative of capital M of x. This means we can make the following substitution on the left. It then follows that capital M of x is an antiderivative of 3/16 times x minus 3 squared. So now we can rewrite our summation formula as follows. The area from 0 to 8 is equal to the integral from 0 to 8 of m prime of x dx, which we know equals capital M of 8 minus capital M of 0. In closing, it is important to note that there are a number of implicit rules governing how the fundamental theorem of calculus takes shape. When we start to build an area under our initial function, little m of x, it is this discrete collection of 8 rectangles that governs what our unknown function, capital M of x, will look like. Our unknown function is limited to a discrete piecewise state of existence. Using rectangles, we can sculpt a very good approximation of the antiderivative. But our unknown function will always be a limited piecewise version of the antiderivative, governed by discrete steps from one delta x to another. Only when we abandon a discrete collection of rectangles in favor of a continuous curve are we able to replace a piecewise version of the antiderivative with a continuous version of the antiderivative. There is an unusual duality about the fundamental theorem of calculus. Even though the slope of our function is now governed by a continuous curve at any given value of x, the growth of our function is still bound by the sequential rules of summation, which are by nature discrete. It is this dual nature of the theorem that allows us to make the substitutions that we do. I realize that this dual nature of the fundamental theorem may still be hard to grasp, but allow me to offer one last thought. Prior to the fundamental theorem of calculus, mathematicians had to resort to some pretty tedious algebra to prove that the limit of this sum converges to the value on the right. To demonstrate to you how tedious that algebra was, consider this. They had to rewrite the sum on the left as such to study how the sum would behave as n approached infinity. This whole expression here, by itself, is an arbitrary value of x, which we call x sub k. I can hear your brain entering deep fry mode. However, if you wish to learn more about this tedious process, I have included an epilogue to this video which explains why we cannot simply write x sub k in place of that red monstrosity below. However, if you feel satisfied that you have a better understanding of the fundamental theorem of calculus, you can stop the video now and say a prayer of gratitude to Sir Isaac Newton and Gottfried Leibniz for coming up with a remarkable theorem that allows us to replace the mess on the left with this simple expression, which in turn evaluates with this simple operation. So you have decided to punish yourself with the ancient methods of infinite summation. Okay, let me begin by setting aside this terrible expression so we can examine a very simple summation with 3 rectangles. This means that we will divide our interval below into 3 increments, so n equals 3. Our interval AB, in this particular case, is 5/8. The length of this interval is b minus a, or in this case, 8 minus 5. Each division has a length of delta x. The the length of delta x is equal to b minus 8 over n, or 8 minus 5 over 3, which equals 1. We now have the tools we need to construct our summation formula. For the moment, let's set aside this little delta x block. Our first rectangle is positioned as such. To help me keep track of each rectangle, let me label each one. Notice that the tip of the rectangle that touches the curve is positioned at x equals 5, which is the beginning of our interval. So x sub 1 equals 5 and k equals 1. Pay very careful attention to this next part. Our second rectangle is positioned as such. However, I will choose to say that its position is x sub 2 equals 5 plus 1 delta x. Here k equals 2. Our last rectangle is at position x sub 3 equals 5 plus 2 times delta x, and k equals 3. The reason for doing this soon will be clear. Let me make one small change to the list of variables below. Notice that the number in front of delta x is always one less than the value of our index variable k. I am now going to derail this simple summation midstream. Suddenly now there are thousands of rectangles under the area below. My colleague forgot to tell me how many rectangles he constructed, so n is undefined. That means that I have to rewrite delta x as such: b minus a over n, or in this case, 8 minus 5 over n, which equals 3 over n. It is impossible to pick out a specific rectangle below, but I do know that whatever rectangle I choose will be positioned at a spot which is 5 plus k minus 1 times delta x units away from the origin. When I go to write my summation formula for the series of rectangles, I know that the height of any given rectangle will be determined at the value of x where its top left corner touches the curve. I have no way of knowing what the value of k is at this rectangle. It may be the 50th rectangle, it could be the 3000th rectangle. I'll just choose to call it k what? K what? K what is a very good rectangle to use when we want to write a summation formula. It can serve as the poster child for all of the other rectangles. The height of k what is m prime of x sub k equals 3/16 times x sub k minus 3 squared. The width of k what is delta x. Thus, the area of k what is a sub k equals 3/16 times x sub k minus 3 squared times delta x. Since we have chosen k what to be the poster child for our summation formula, we can write that summation formula as such: area equals the sum from k equals 1 to n of 3/16 times x sub k minus 3 squared times delta x. If we make the following substitution, the formula looks like this. This is where the tedious algebra begins. I will not be narrating this portion of the video, but feel free to stop the slides at any point to check my algebra. As you can see, this matches what we found using the antiderivative. But thank goodness for the fundamental theorem of calculus.